Today I will talk about how to prove vector addition experimentally. But before to go and do that, we give a quick introduction to vectors. So in engineering and science, we divide the quantities to two main groups, whether scalar quantities or vector quantities. So two main groups, whether scalar or vector. So for a scalar, we need only the quantity, the magnitude. So for a scalar, we need magnitude. But for vector, we need both of them. We need magnitude, but we need also direction to specify it. And there is also two ways to work it out, whether graphically or mathematically. So when we solve it graphically, we use arrows. So an example of a scalar is time, mass, length. An example of vector, velocity, force acting on a body, and so on. So if we have a force, we want to represent it in an arrow, so we need to know the direction and the magnitude, so how many bound force and in which direction. If we say this is north, so this will be, say, east. Okay, so we'll say for example 5 bound force in east direction. So this is the way that we add or subtract vector. And if we have around 3 forces, we can draw some space diagram, and after that we can draw something called triangular forces. And if it is more than 3, if it is 3, triangular, okay, something like this. If it is more than 3, say 4 or 5, then we do a polygon of forces. So we do any type of polygon, say something like this. Okay, and the forces should follow each other, so head to tail. So if we start here, say if this first force, then second would go this way direction, second one this way, like this. They follow each other, and when they close like this, we say they are in equilibrium or in the triangle as well. So when we're solving, we will find the resultant. So let us go to our experiment now. So for this experiment, to prove vector addition experimentally, you need these things actually. So you need a vertical board, the one shown here, this one, and we need also 2 pulleys. And if we don't have pulleys, then we can use round nails. So with the board with the same board, and we need also 3 threads. So we put for each forces, if you can hear, for each weight. So for weight number 1, we have 1 thread. Weight number 2, another thread. Weight number 3, another thread. And we have to make a knot in the middle, so all of them come through the same point. And from the experiment, if we have a compass, we can measure the direction here. So we can make a line here, horizontal line. Let me change the color. So if we make a horizontal line here, so we can measure the angle here and here, and this should be vertical, and so it should be this 9 degree, okay, with this horizontal line. So if we know these two angles, then we will know the direction. And each weight number 1, 2, and 3, they are exerting tension on this thread here. So weight 2 exerted tension here in this one, on this direction up. Weight 1 exerted here, up direction. Because the weight is pulling down, so the knot here is pulling, because the weight is pulling down, so the direction is going there. Yeah, and this is the point where the line where all the forces come across. So this one also pulling down, so that means there is a force exerted in this direction, this direction. So after we put the different weights here, 1, 2, and 3, we make sure the thread is not moving. Then if we don't have a compass, we put it here. We can put an A4 between the board and the thread, and we can make lines. So similar to this one. So we can make a space diagram in A4 with a pencil or a pen. So we will know the direction without measuring the angles. Okay, and as we look here in this space diagram, so the first force 2 in the same direction, so should be parallel to it. And this one, weight 3 the same here, and weight 4 number 1 the same. So from our space diagram, we can make our triangle of forces, because we have 3 forces, W1, W2, W3. So in the same way, if we are working with in scale, so this scale could be suitable. So each one distance here give us 1 bound force. Okay, and then we convert this force to distance here in the triangle. So this one, say 4 lb for bound force. Okay, and this one could be around 3, and this could be around 4 as well, or 3. So we convert it to length, so we draw it, but we have to keep the direction. So the direction, this is W1 down. We took this one in the same direction to put it here. Weight number 3. Weight number 1 in the same direction, we put it there. So if you look to this one, that means we build the triangle in this side of the space diagram. If we build it in this side, so we have another option to build another triangle of forces. So this is not the only option, but this is the way that you could prove that vector addition experimentally and mathematically or graphically. So this is the way that you can prove it in the lab. Hopefully that is will help you before you go and do your lab. Thank you for watching.